Okay, ChemQuest 10, Bohr's atomic model. Bohr's solar system model of the atom. All the planets are attracted to the sun by gravity. The reason that the Earth doesn't just float out into space is because it is constantly attracted to the sun. Similarly, the moon is attracted to the Earth by the Earth's gravitational pull. So all of the planets are attracted to the sun, but they never collide with the sun. Negative charges are attracted to positive ones. Therefore, the negative electrons in an atom are attracted to the positive protons in the nucleus. In the early 1900s, scientists were looking for an explanation to a curious problem with their model of the atom. Why don't atoms collapse? The negative electron should collapse into the nucleus due to the attraction between protons and electrons. Why doesn't this happen? Scientists were at a loss to explain this until Niels Bohr proposed his solar system model of the atom. So consider swinging a rock on the end of a string in large circles. Even though you are constantly pulling on the string, the rock never collides with your hand. Why is this? And I want you to consider that, okay? Why does the rock never collide with your hand? And it's because it is moving outward due to the swinging action of the string. It always wants to go outwards. It's the inertia, if you remember that from ICP. The object wants to go out, but the string keeps pulling it back in. So you're pulling on the string, but it has an outward motion. And so what happens is this is what causes it to circle or go around. So even though the Earth's attracted to the sun by a very strong gravitational pull, what keeps the Earth from striking the sun? Well, same idea. The Earth, the Earth's inertia or straight line motion is forcing that to happen. So the Earth's straight line motion, STRAI, straight line motion, is causing this to happen. And we'll kind of give you an idea of that here in a second. So why doesn't the moon strike the Earth? Same idea, right? The moon is also going to move in a straight line motion. And then how could it be possible for electrons to not collapse into the nucleus? Well, the reasoning behind it and what Bohr said was that because the electrons are also moving in straight line motion. And we will try to demonstrate that. So I'm going to use this little diagram here to kind of show you why this rotation around the planets around the sun, the moon around the Earth, and then, of course, the electrons around the proton occurs. So consider this hand here in the middle to be the nucleus where the protons are. Here's the electrons. There is an attraction here. Okay, it's like a ball on a string. As you start to spin, though, or as you start to put pressure on the string, the ball doesn't go that way. Instead, it starts to go this way, okay? And it then forces itself to go somewhere in between of going straight out or straight in, which is then this curved path that we see, so the orbit that we see. So it's a combination of this, which is the inertia of the ball, and the pressure of the string, or we could say this is the electron's inertia, and this is the attractive force from the nucleus pulling it in. So it's somewhere in the middle, and then these two things combined give us the orbit that goes around the nucleus. Okay, so light. Recall light is a wave. White light is composed of all the colors of light in the rainbow. All light travels at the same speed, which is 3.00 times 10 to the 8th meters per second, and we call that the speed of light, which is c. Now this is speed of light in a vacuum is equal to that. It'll vary based on other places besides the vacuum, but it's pretty close to that. Different colors of light have different frequencies and wavelengths. So F is frequency, and then this funny thing here is called a lambda. That is what we use to show wavelength. So the speed, frequency, and wavelength of light can be related to this equation. Speed of light equals frequency times wavelength. It is important that the wavelength is always in meters, the speed in meters per second, and the frequency is in hertz. Now a hertz, okay, it just means per second. So that means how many times it revolves per second is when we talk about the frequency, or bounces per second, all right? So let's think about this equation and look at number 5. It says as the frequency of light increases, what happens to the wavelength of the light? So as the frequency increases, so if C stays the same, if I increase F, wavelength will have to go down or decrease, okay? What is the frequency of light that has a wavelength of 4.25 times 10 to the negative 8 meters? Do it now.
What is the frequency of light that has a wavelength of 4.25 times 10 to the negative 8 meters? All right, so the equation C, speed of light, is equal to frequency times wavelength, and that's for all light, all right? And we're talking about light here. So we're actually talking about C being, and the number they give you, I'm okay with this, 3.00 times 10 to the 8 meters per second. That's your C. And then frequency and wavelength. And we know the wavelength in this case is 4.25 times 10 to the negative 8. So I just make an equation, and I go 3.00 times 10 to the 8 for this is equal to frequency times my wavelength. I got to look again, 4.25 to the negative 8, okay? So 4.25 times 10 to the negative 8. I divide both sides. And that will give me my frequency. So let's get the calculator out and take 3e8 divided by 4.25 e negative 8. And I get a frequency of 7 points. I'll go 3 times 10 to the 15th. And our unit for frequency is hertz. So that is the frequency of our light in this case.
What is the wavelength of light that has a frequency of 3.85 times 10 to the 14th hertz? Do it now.
What is the wavelength of light that has a frequency of 3.85 times 10 to the 14th hertz? So just for the opposite now, we have frequency. We're going to solve for wavelength again. The speed of light is a constant. And my frequency is 3.85 times 10 to the 14th. And I'm solving for wavelength. I just divide. And I get wavelength. And when I do that, calculator, 3e8 divided by 3.85 e14, and I get a really, really small number. I'm going to write it out two ways. It's like there's 6 zeros. 1, 2, 3, 4, 5, 6, 7, 7, 9. Or I could write it in scientific notation. I move the decimal 1, 2, 3, 4, 5, 6, 7. But either way, it's meters, and either answer is fine.
Energy levels. After Bohr proposed the solar system model that electrons orbit a nucleus just like planets orbit the sun, he called the orbits energy levels. So looking at the Bohr model here, in the center, we have our protons and neutrons in the nucleus, and then you have your electrons. There's one energy level, here's the other. Higher energy levels are further from the nucleus. For an electron to go into a higher energy level, it must gain more energy. Sometimes the electrons can absorb light energy. Just know that different colors of light have different frequencies and wavelengths. If the right color, and therefore frequency of light, is absorbed, then the electron gets enough energy to go to a higher energy level. The amount of energy, E, and the frequency, F, of light required are related by the following equation. E equals H times F. E is energy in joules, F is frequency in hertz, and H is called Planck's constant. And it's in the units of joules hertzes, which is the same joules seconds. Planck's constant h always has this value, 6.63 times 10 to the negative 34, a really, really small number, but that always is going to be h. An electron that absorbs energy and goes to a higher energy level is said to be excited. If an excited electron loses energy, it will give off light energy. The frequency and color of light depends on how much energy is released. Again, the frequency and energy are related by the above equation. When an excited electron loses energy, we say that it returns to its ground state. Since not all electrons start out in the first energy level isn't always an electron's ground state. So the ground state is where it starts, and excited state is the energy levels it jumps to. So number 8, does an electron need to absorb energy or give off energy to go from the second to the first energy level? Well, to go down from the second to the first, it needs to give off energy. How is it possible for an electron to go from the third to the fourth energy level? It needs to gain energy, okay? So let's type those in. Here we got to absorb, to go from the second to the first, it needs to give off energy. And then for how is it possible for an electron to go from third to the fourth energy level? It needs to gain energy. Number 10, red light of frequency 4.37 times 10 to the 14th hertz is required to excite a certain electron. What energy did the electron gain from the light? Do it now.
All right, red light of frequency 4.37 times 10 to the 14th hertz is required to excite a certain electron. What energy did the electron gain from the light? If we're talking energy, we're talking this equation, E equals Planck's constant times frequency. And so I know wavelength, or I know frequency, so I just want to find energy. So I just pretty much substitution. So my energy equals Planck's constant, 6.63 times 10 to the negative 34, multiplied by the frequency provided, which is 4.37 times 10 to the 14th. And my energy will be 6.63 e negative 34 times 4.37 e 14, 2.90 times 10 to the negative 19 joules, which not a lot of joules, right? It's a really, really small number, but that's your answer.
The energy difference between the first and second energy levels in a certain atom is 5.01 times 10 to the negative 19 joules. What frequency of light is necessary to excite an electron in the first energy level? Do it now.
All right, so the energy difference between the first and second energy levels in a certain atom is 5.01 times 10 to the negative 19 joules. What frequency of light is necessary to excite an electron in the first energy level? So we know energy, and we want to solve for frequency. So I know energy, want to solve for frequency. And H is, of course, Planck's constant, so I just substitute and go. So E is 5.01 times 10 to the negative 19 equals 6.63 times 10 to the negative 34 times F, divide by Planck's constant, and I'm solving for frequency. So 5.01 E negative 19 divided by 6.63 E negative 34, 7.56 times 10 to the 14th, and we're talking frequency, therefore it is hertz.
12. What is the frequency of light given off by an electron that loses 4.05 times 10 to the negative 19 joules of energy as it moves from the second to the first energy level? Do it now. And part B, what wavelength of light does this correspond to? We will do that one now.
All right, so number 12 has two parts. What is the frequency of light given off by an electron that loses 4.05 times 10 to the negative 19 joules of energy as it moves from the second to the first energy level? And then part B is what's the wavelength. So we're going to use both equations here. The first equation is energy, and and we know the energy to be this equal to Planck's constant times frequency. So I can find my frequency. And my frequency is times 10 to the 14th hertz. So there's the answer to A, frequency. So now I know frequency, and I want to find wavelength. So I take my frequency answer, and I put it into here, solve for this, knowing that C is the speed of light. So I know 3.00 times 10 to the 8th is equal to my frequency times wavelength. Exponent 8 divided by 6.11 exponent 14. And again, we're going to get a really, really small number like we did before, 6 zeros. And the numbers, or, but same answer. And it's in meters.
13. Do atoms of different elements have different numbers of electrons? And of course the answer is yes. If it has 12 protons, it has 12 electrons. If it has 13 protons, it has 13 electrons. Different atoms have different numbers of electrons. We've talked about that already. 14. If all the electrons in atom A get excited and then lose their energy and return to the ground state, the electrons will let off a combination of frequencies and colors of light. Hopefully we can show you that in lab this week. Each frequency and color corresponds to a specific electron making a transition from an excited state to a ground state. Consider an atom from element B. Would you expect the excited electrons to give off the exact same color of light as atom A? Why or why not? And long answer short. Try to make it short. It would definitely be different colors, and it's because atom A and atom B are totally different elements. So they have, because they have a different number of electrons. So therefore they'll give off different colors. And we will use the flame test to kind of prove that.